everyone. Welcome back to the latest lecture session. In the last couple of sessions, we were discussing rather in detail, if I may say so, coagulation and relevant aspects, and we looked at lessening or decreasing this electrical double layer thickness by various ways. And one of the ways was charge neutralization and interparticle bridging, and the other one based on the type of coagulant you are adding was sweep coagulation. So in that context, we looked at interparticle bridging. I think there was a pretty good figure that we looked at. So in general, you will also, or you can add polymers that can lead to formation or lead to this kind of interparticle bridging, right? Let's take this through. So you have organic polymers that can be added. Organic polymers, again, there are two kinds based on the type of polymers. So cationic, we know that the colloid is negatively charged. So if you add a cationic polymer, cation meaning positively charged, what can it do? It can either neutralize after adsorption, or also it can form a bridge. So first it is going to adsorb and then neutralize depending on the charge, and it can also form a bridge with respect to or with the other particles. So you will have both neutralization and interparticle bridging. You can also have anionic polymers. There are also non-ionic polymers where the primary purpose is to act as what do we say, bridging agent, if I may say so, or to promote interparticle bridging. Here we are looking at anionic polymers. So when can we use them? When we say that the other coagulant, let's say cationic polymer or any other cation itself, has been overdosed. You saw that with respect to electrophoretic mobility and such, if you overdose it, this is the picture. So somewhere here is the sweet spot, right? And if you overdose it, then you have to bring down the charge, then again anionic polymers or such. Or you can also add them just for bridging purposes, let's say. So that's the aspect that we need to discuss here. So how do I know what is the dose to be added, right? For example, with respect to ferric hydroxide or aluminum hydroxide, we saw the relevant graphs, and we saw that at different regions, as in different pH, different aluminum, different ferric iron concentrations, different types of iron or aluminum will predominate. So how do I know in my what do we say scenario, which one do I want, or which concentration do I want, whether I primarily want to go with sweep coagulation, or will charge neutralization also play a role or such? Here it will depend on various factors, one NOM and other species. So analyzing what's there and such is remarkably difficult, or not difficult, time consuming and costly, I guess. That's the major aspect. So we are going to conduct a simple test, right? How am I going to optimize the coagulant dose? So we conduct a test which is called a jar test, let's say. Let's see how we will go about it. So it's simple. I'm going to take the sample, and here what are the aspects of interest? We remember that pH plays a role, because depending on the pH you can have the precipitation occurring, or you can have different charge out there. So you can vary two primary variables. One is the charge, not charge, charge indirectly by the pH, and also the coagulant dose. So these are the two aspects you will check while conducting these jar tests in the lab. So you will take the actual water and conduct the test, let's say. What are we trying to do? We are trying to simulate initially coagulation and then flocculation, let's say, right? So let's go forth. Here we are looking at two aspects, coagulant dose and even mixing rate. But primarily for the jar test, we are looking at coagulant dose. Mixing rate and such will also depend upon the kind of mixer or impeller or such you are using in your particular system, and the dimensions of your system and such. So coagulant dose primarily. So this is what it looks like. Most UG labs would have had it. What do we have? We have this mixer, that's dipped into this solution. Okay, here you can see a clearer picture out here. It's a blade out here. So whatever are you going to do? We are going to take the apparatus with the water or the sample that you want to conduct the test upon. So 3 samples or 6 depends on the kind of test, let's say, right? So again, one thing is here people took the circular beakers. If I look at the plan view, this is the thing. But for greater turbulence, if you take square or rectangular ones, that's better. But in general, these are difficult to maintain, easier to maintain. So that's why people use the circular ones. That's something to keep in mind, right? So you can see the flocks being formed and maybe later settling out. So different stages of coagulation and flocculation. So what's the procedure? Obviously, I want to, test a range of doses with different kinds of coagulants, right? So then what do I need to do? I need to form, what do we say, have coagulation. For this, I am going to mix it, as in create considerable turbulence so that the coagulant mixes well with my solution and will either absorb and neutralize the charge or precipitate. Again, we will look at that later, or have some interparticle bridging. But again, that's only initially. If you mix it too high, you know that again interparticle bridging will be affected. So rapid mix for a small amount of time so that you have good mixing. And then you will go to slow mix. Why? You want to promote flocculation. If you continue with rapid mixing, the flocks are going to either shear, or we looked at the issues with respect to the polymer, binding itself with the same particle and such. So we'll have to look at slow mixing. Initially, we want coagulation occurring here, and then during slow mixing, flocculation. So then we are going to let it settle down. What am I trying to do? Coagulation and flocculation, and then settling, right, or sedimentation. This is what I am trying to simulate in the lab. So then I will test the sample for turbidity and also pH, because after addition of alum or some of the other coagulants, you know that the pH will decrease. You want to see whether that pH decrease is acceptable or not. So thus you will measure pH. Turbidity is our primary aspect or concern, as in we are trying to measure how much suspended solids we were able to settle down. So obviously I will measure turbidity. In India, we don't do this, but if we are able to remove some natural organic matter which will affect the DBP formation potential, that also you can measure. And volume of solids, how much volume of solids or such is produced. Why? Because in the actual treatment plant, you will have sludge being settled down, and that sludge you will have to take care of it again. So you want to be able to calculate that. So optimal coagulant dose, and here the aspect is that it's not always the minimum. It's obviously balance between practical aspects such as the costs and the final turbidity that you want to achieve, let's say, right? We are not looking at the ideal case scenario. So that's one aspect to keep in mind. So what do we have? Typically 6 beakers with the sample, and then we are going to have rapid mixing, right? And then flocculation and with slow mixing, yes. And the kind of mixers are going to be the same throughout. We looked at the picture earlier, identical paddle stirrers, and in general by a single motor, let's say, right? So what do we do in the first test? I am going to either change the pH or the dose. Typically, I will keep the pH constant and vary the dose. So that's what we see. Okay, so depending on it, people will go about it the other way, but typically if we look at the effect, it's always better to keep the pH constant and then look at the dose, but again different ways to go about it. So then I am going to find the optimal pH and the coagulant dose. So first people are looking at the pH and then using that optimum pH to find the optimum coagulant dose, right? So let's see how we can go about it. So we have a jar test here. We have the 6 samples and pH was varied from 5 to 7.5, and the alum dose was fixed at 10 milligram per liter. Obviously trial and error initially too, as in I am not obviously going to go to too acidic or too basic pH. It will depend upon my objectives too at the end of the day, and the cost of neutralizing this. Again, I am not going to release, even if the turbidity is lowest here, I am not going to use that, or probably might not. Why? Because to neutralize it, bring up the pH to 7, I need to add an OH or such. Again, concentration, not concentration, costs are involved. So these are the aspects to be mindful of. And then alum dose is kept constant, and then we are measuring the turbidity. You see that the turbidity, well, decreases and then increases again here, right? So here it's again a mix of what is this? Optimum charge neutralization and sweep coagulation, maybe depending on the type of alum, but again here it's just alum, maybe less of interparticle bridging, let's see. So what do we see? We see the effect of pH, and so you can choose either 6.5 or 6, and I think based on the data we will choose 6. Okay, so based on the data we are choosing a pH value of 6, let's see, and then you are going to choose that pH 6 and keep that constant across all your samples. Now you will conduct the test again at this pH across again 6 samples, and now you are going to vary the alum dose 5, 7, 10 and so on. Let us see, again trial and error is obviously involved, and then I will get the residual turbidity. This is the turbidity of the solution that is remaining, right. And here we have the effect of alum dose at constant pH, right. So, that is what you see out here, and then we see that this is the profile. From here you can choose the relevant concentration, but in general, because the range is considerable, what people will do is they will conduct a test again with values chosen in this range, let us say, right, so that you can get the accurate concentration. You do not want to put in too much alum, right. To be able to capture the most optimum one, you will typically conduct the test, right. So, we looked at this. So, looks like pH 7, we already looked at that, and people were choosing 12.5, but again as I mentioned, in general you will conduct a test again, let us see, right. And depending on your objective, sometimes you can even choose this. After you choose this particular coagulant dose, you can again conduct the effect on the pH, as in is there a better pH, let us say, but again it obviously is slightly time consuming. It is not a lot though, it is pretty fast, because we are only talking about a few seconds, but for settling maybe a few minutes. So, it is not very time consuming, but again in general if you repeat it, it is going to be an issue. So, there is some trial and error involved, and depending on how accurately you want to capture the effect of pH, you can repeat it for pH, but that is rarely done. So, rapid mix design, right. When I say rapid mix design, what is it I am concerned with, at least at our level. So, I want to promote mixing, right. How will I promote mixing? I want to create turbulence. Turbulence meaning if let us say water is flowing in this direction. Let me put it down on the paper here. So, water is flowing in this direction, and everything, or if it is laminar flow, right, everything going at the same velocity or such, and then there is little to no mixing here, right. But if I have different velocities or such, yes, in different directions and such, I will have eddies being formed, and then mixing of layers and such. So, I want to create this differential velocities or velocity gradients. So, if the water itself does not have sufficient gradient or turbulence, what will I do? I will create that. So, for example, think of it in your home. What do? We turn on the fan. Similarly, you can have different types of mixers or impellers here. So, here there are two aspects. Let us say I am it's a bit sultry and I want to turn on the fan until I feel comfortable. So, two aspects, either I increase the fan speed to the highest possible and feel comfortable in a relatively shorter amount of time, or maybe at lesser intensity for a longer period of time. But again, it is not a straightforward analogy, but what I wanted to point out was the level or mixing intensity and the time or the duration for which you are going to mix both play a role. Obviously, here we are limited by the kind of energy we want to impart. If you give too less an energy or such at this point during coagulation, the system will not mix well. But again, what are we concerned with? Intensity of mixing and how long will you mix it. So, how is it that energy is transferred from the larger scale to the smallest scale? Let us see. Let me look at this figure that is presented in Crittenden et al. So, here I am going to start my motor. So, large scale action sets water in motion from my impellers or fans in the water. So, I am going to form eddies, and this eddies lead to transport of the energy, right, from one eddy to the other into smaller and smaller eddies, let us see, right. And here we see that there are two aspects, macro scale and micro scale. We will come back to this earlier, but please do understand this figure. Here motion is turbulent, right. Energy transport is due to inertial forces, as in some water is still, others are in motion, right. So, you have inertial forces, and eddies influence the design of mixing device and level of energy input. Flock will break up. So, obviously, here at this level flock will break up, and then inertial subrange is not affected by the viscous forces. Eddies influenced only by the level of energy input, right. And then we come to the smaller scale where eddies do not form, right, and here it's viscous energy dissipation, let's say, right. So again, eddies, transfer of energy, let's see. So that's one aspect to keep in mind. Yes, initially the large scale motion is relevant, and later that large scale motion is not that relevant, let's say. Yes, so eddies in one region and no eddies, but again micro scale mixing, which is important for smaller particle, and macro scale for the bigger particle. So what is the goal? I want to quickly mix them so that the coagulants can destabilize the colloids effectively, let's say, right. So we have different types. So what do we have? One is the inline blender, right. That's what you see, inline mechanical blender, or also known as inline blender. So you have water coming in and going out. You can add a chemical feed, okay, chemical is being added from here, and you have this propeller or impeller here, let's see, and you are going to have mixing in here. And next is inline mechanical, again different types, so we will not go into that in detail. Other one is static, no moving parts, that's obviously a relevant advantage, and thus no external energy source is required. Looking at the design, you can see that the water mixes, I guess, right, different elements, differently sized elements, from a few centimeters to maybe even 100 centimeters, but rarely, I guess. That's for industrial zones, industrial types. So this is static. The earlier one, obviously, as you see, was mechanical. And we have another one, stirred tanks. Well, it depends on the system, depending on the space. If you don't have space, you will go for inline. If you have space, and depending on the level of control on the mixing, maybe you will go for your stirred tanks. So stirred tanks, obviously, so flow is coming in and flow is going out. What is it? It's a completely mixed flow reactor or a continuously stirred tank reactor. And in general, looks like we will promote sweep coagulation, right. And here we will also have horizontal baffles to minimize short circuiting, as in depending on where the water is coming in and where it's going out, you don't want the water to take the shortest path, you want it to be well mixed, right. So we want to prevent short circuiting, that is why you have these baffle walls, I guess, right. So let me see that. Okay, here you have the baffle walls, you have the mixers. So chemical addition is taking place at different stages, and the water is coming in here and it's going out. So completely mixed system here, right. So let's move on. Again, the types of mixers here, let's see, right. So mixing equipment consists obviously of a motor and speed reducer or regulator, and either radial flow, this is radial flow, right, think of this, and this is axial flow, right, different depending on the type of flow, right, radial flow or axial flow impeller. Again, why is this relevant and such? Because depending on the relevant area here, the design, you are going to have what do we say, shear forces being generated that lead to turbulence and such, and obviously the energy that you are putting in through your motor, for which you are paying, will have to be able to do the job efficiently. So that's where the design comes into play, and we will look at this soon. Okay, primary design variables, as I mentioned, one is the how much time am I mixing it for. When I say time, it obviously refers to the time that this water is spending in my system, right. Time the water is spending in my system, and we know that it's called the hydraulic retention time. Theta equal to V by Q, you can calculate that pretty simply. And what's the other one? It's about the intensity of mixing, right. Intensity of mixing. How will I be able to achieve that? We know that we talked about, different velocities, or you want to have a gradient or difference in velocities at different levels. That's when you will promote mixing, let's say. So that's what we have out here. So this is the figure. Let's say here there is zero flow, and after creating the right conditions, I have this velocity gradient. So here I am saying that the velocity gradient is dv by dy, or let's say for the sake of uniformity, in the case of other pictures, let's say this is dv by dz. So this is the mean velocity gradient. What is the gradient in velocity? Here it's 0, and here the velocity is increasing. So there is a gradient in velocity. What is that, or what is the variable? It's g, and it's called mean velocity gradient. So it's in this direction. That's what this is, z, I guess, right. So that's something to keep in mind. The velocity is 0 here, and it's increasing with what do we say, or increasing with z. So let's see how to go about it. Crittenden et al. Gives this. So you have this particular what do we say, section, if I may say so. And here the velocity is v. Above, we know that velocity is increasing as we are going up. So v plus delta v is out here. So you are going to have force here, let's see, right? And that force is, again, this is from Newtonian flow, tau xy. This is on this plane, xy plane. This is x and this y on this plane. What is the force being applied? Tau xy into area, right? And that's going to be equal to, this is from Newtonian flow, mu dv by dz, right? How is the velocity changing? And delta x, delta y, right? We will look at it in a different way too, but I wanted to present this aspect here. And power, we know it's force into velocity, power per volume. So I want to calculate power per volume. Force into velocity, volume is delta x, delta y and delta z, that's what we have. Force, we just calculated that here. Force is what we calculated that from here. And what is the velocity, let's say, at any particular height? We know that the velocity gradient is dv by dz, and at a particular height delta z, it will depend upon the rate at which the velocity or the rate at which the velocity is changing with z. So velocity is equal to dv by dz into delta z. So if I simplify this, looks like this is what I will get. Yes. And please note that we said that this g is the mean velocity gradient, So this is what we have here, g, let's see. So what is a different way to, so this will give me an idea about the level of mixing. So a different way, again, this is from Dr. Batchelor, but the person who looked at it or presented this was Dr. Camp. So Camp analysis, we are assuming laminar flow conditions. That is what we saw 2 slides before. And we are assuming that the flat area, let's say, which was delta x or in the xy plane earlier, is being pulled at a velocity v near a stationary surface and distance L away. This is in the z direction. And the viscosity is mu. So under laminar flow conditions, right? It's under laminar flow conditions. So what is F by A on that particular plate in the xy plane? So it's similar to what we have. What is F by A here? F by A, it's mu into dv by dz, similar to what we had earlier. So F equal to mu A dv by dz. I'm just presenting the previous information in a relatively better manner, which can be easily understood, let's say, right? So earlier A, we took that to be delta x into delta y, right? That's something to keep in mind. And power consumption, power is force times the velocity, let's say. And laminar flow, what does that mean? Let's say here we saw that in the 2 graphs before. Velocity at this place is, or location is 0, and it's increasing at what rate? dv by dz. So velocity at particular height L will be given by the rate of change of velocity with height into L, let's say, or dv by dz into L. So from here I can calculate the power equal to F into V, that's equal to mu A dv by dz, and thus, so that's going to give me, and I can transform this, and from here I will get this, G is equal to dv by dz, that's equal to the square root of the power, right? That's where you are, that's what you are imparting from your pump. V is the volume of that particular section, and mu is the dynamic viscosity of water, right? So that's something to keep in mind. And how do I relate this to the different kinds of mixers or impellers out there? We will look at that, let's see. So by impellers, I am talking about these different kinds of impellers. Note that, the angle, there are different kinds. For each one, there is a power number. Keep that in mind. And then the application is also given here, blending viscous liquids, blending and maintaining suspensions, and for flocculation and such, let's say, right? So for blending, it can be used for both blending or coagulation and flocculation. This is what I'm talking about when I say impellers. So power number is given, it is a constant for turbulent flow, and the power consumed, let's say, which will depend upon or which can be related to power number, right? And thus we just saw it is calculated by the relevant manufacturer. It's going to be depend upon the power number, the rotational speed, as in how fast is it rotating, right? You have different impellers, how fast is it rotating, the diameter obviously of the impeller, and the density of that particular water, let's say. So from that you will get an idea about the power consumption that's required, let's say. and then you can relate it to G and such. So inline mechanical mixing, how do I do that? Either with mechanical mixing or even static mixing, how do I get it, how do I relate this power, let's say, and G? How do I get that information? So we should understand that inline we are going to have a head loss, and head loss is nothing but energy that's lost or dissipated per weight. And we know from Bernoulli's equation, head loss is equal to this, right? So P is pressure here, not power. P here is pressure, right? Head and V square by 2G. And here I want to remove this weight term. So let's see how we can do that. Q into rho, or I'm going to get Q rho G. This is, what is this, volume per time and mass per volume. So I'll get mass per time or weight per time, right? Because it's G, it's not mass, it's weight per time. That's what I'm going to calculate here. And now energy dissipation. So if I want energy dissipation, let's say, how will I get that? Which is P, this is power, Q rho G, which is weight per time, weight per time into energy that is dissipated per weight, which is head loss, right? So that's what we have, Q rho G into HL. So Q into this particular variable and HL, let's say, right? So from this I will be able to calculate this, and I know that G is equal to square root of P by V mu, and I can get a relationship between G and the relevant aspects out here, let's say, right? So let me just erase this side. Okay, from G, the level of mixing based on the relevant head loss and the hydraulic retention time, right? So that's something for you to look at, because we know Q by V is equal to or V by Q is equal to theta, right? So again, we are looking at the power dissipation, let's say, right? I'm putting in power and I want to be able to understand how is it being dissipated and how much level of mixing I'm going to get. So that's what we are trying to understand out here. So I'm out of time. We will continue the next aspects in the next session. But what have we looked at until now? We have looked at different types of mixers, and we know that how much time the water spends in the system is of primary importance, which is theta. And we also want to know how much turbulence it is or how much mixing is needed. For that, what is the variable we are using? It's called G, mean velocity gradient. Velocity gradient meaning change in velocity, let's say, right? So we were able to also then look at energy dissipation. How is this energy dissipation, relevant to either head loss or G, so that I can understand and design accordingly. So with that, I will end today's session. Thank you.